Alrighty, I believe it is time for us to kick this off. So we have so much to cover. I'm going to go ahead and start. Feel free to keep on coming if you're waiting in line. There's lots of seats up front here, so yeah, welcome, welcome. My name is Randy Abernathy. I'm a managing partner at RxM, and this is Kubernetes Networking 101. So let me just see a quick show of hands. How many people would consider themselves very savvy Kubernetes networking people? All right, so everybody else, if you saw someone raise their hand, you got questions, you know where to go, right? It's those people. So yeah, this is going to be a super fun tutorial. We have 90 minutes. We have a ton of stuff to cover, and I'll just give you a quick intro to the format. We have stood up hundreds of machines in a cloud provider who shall remain nameless since they wouldn't sponsor us. And so you guys can SSH into the box that you were provided on this sheet. Now, I realize that we're on conference Wi-Fi, right? We all know what that means. It's probably really banging, great Wi-Fi, but there's 200, 300 people trying to use it all at the same time. So the best thing that we could do is, instead of you downloading all sorts of packages and containers and stuff that would be really slow, you can just SSH to these cloud instances and send a few characters back and forth every once in a while. It's the lowest bandwidth thing that we can come up with for a session like this. It's also really great because if you completely thrash this computer, your laptop is still fine, right? So don't worry, right? It's a virtual machine. And if you do completely thrash this computer, we have spares. So I have three folks helping me today, Chris, Ilian, and Valentin. And Chris is, by the way, doing a talk at 1600, Kubectl Said What, which is going to be super awesome, so I would go to that if I were you. But those guys are going to come around and help with questions. So if you have a question, raise your hand. Those guys will be scanning the room. They'll come to you. They can give you a new machine if you need it. We got spares. They can help you get unstuck if you're working on a part of the tutorial that isn't working. We've tested it a bunch of times, so I feel pretty good about if you read the tutorial steps carefully and do them the way that they say, it's going to work. Hopefully we won't have too many problems, but we're here to help. If you have any questions at all, feel free to ask. Yeah, question. Great question. So when we get to the first lab break, I'll go into this in some more detail, but the question was, hey, I don't have my laptop, or my laptop's locked down or something, and I can't get to these boxes. What do I do? Well, you can, we're going to have some slides and presentation, and I'll probably do a lot of the steps if I have time while I'm running around, so you get to see that. But also, there's instructions in the lab as to how to stand up a plain vanilla Ubuntu 2004 server that you can do the labs on. There's nothing special about these labs. They're just running on a plain vanilla Ubuntu 2004 server. We literally start from the absolute start, install Kubernetes, set up CNI, start creating services, install the service mesh, install the, the ingress. Everything is right in that lab. So it'll be really easy to redo later. Also, and I appreciate that question, because hello, virtual people. All the people who are, over here. Hello, virtual people. All the people who are online, obviously, you didn't get one of these sheets with an IP. There's like 800 people or something signed up, so we couldn't do it for everybody. But if you've got a box that you can use that's a plain vanilla Ubuntu box, a VM, you can just either SSH into that. If it's in a data center, it's on your laptop. If it's in a cloud somewhere, that's going to work fine. And there are instructions for doing exactly that in the lab. Right? The lab points you to a virtual machine setup doc, which is a markdown on GitHub, and you can follow the instructions there to run a basic VM that we already provided for you. It's just a plain vanilla Ubuntu box again, but you can stand that up and do the labs. So yeah, great questions, and I'll continue to give you more information about the lab as we close in on getting started on the first step. This session is organized into 5 parts. We're going to take about 15 minutes for each part, and then I've got a very tight budget here to get started. So we're going to do like maybe 5 minutes of discussion, and then 10 minutes of lab work, 5 minutes of discussion, 10 minutes of lab work. This is a hands-on session, right? This is a tutorial, so you're going to be doing all of this stuff. And I'm only going to give you the overview because you're going to do it, right? Why should I tell you the commands when you're going to type them yourself? So all right, so that's it. So these 3 guys are out there ready to help. Also, you'll see that there is a tutorial lab doc in the slide deck here. It's also on your sheet. So for the virtual people, you can get this deck off Schedule. So these slides are on Schedule already. So if you go to the talk, you see the schedule, the slide link, click that, you'll get this doc, and then that link will take you to the Markdown. So let me just preview that Markdown for you real quick, make sure everybody is able to find it. It looks like this. The link, it takes you to KubeCon EU 2022. So the full URL is github.com/rx-m/KubeCon-EU-2022/tree/main, obviously. And then if you click on the Markdown, it's just going to open right up. That's the lab, right? And you'll notice that it's broken up into steps. So step 1, our first lab session is going to be pod networking. And that doc's not going anywhere. That'll be there forever. So you can look at that in 3 years if you want to. Nothing will work, I'm sure, but you could try it. OK, so that's a bit of the startup. Hopefully now everybody's got a sheet with the IP. The other thing you're going to need to log into the lab system, you need an IP address, right, to reach the host. And then you need to prove your identity. And so you're going to be Ubuntu, big surprise, right? That's your user ID. And then you're going to need a key. And that key, the link for the key is on here too. Right? So here's a hint also. It's the same key. So if somebody needs help, you can log into their machine. Right? These machines are all going away in about 2 hours. So all right, that's enough of the logistics. Let's talk about the talk. So our goal is to introduce the world of Kubernetes network communications in a high level but practical way. The idea of each of these little thought experiments, these little labs, is to show you how a part of the Kubernetes networking world works in enough depth that you understand it and you could walk away and go, cool, I'm not a networking person, but now I get it, and everything's going to be a lot easier for me because I understand all these little parts. Or if you are interested in digging deeper, you have a beginning point, right? We've installed all the stuff. Everything works together. That's a lot of times, the big time waster. Now you can get down to the business of playing with it and experimenting and taking your journey further. So that's the idea behind this session. Concepts and projects that we're going to explore. We're going to begin with container networking and talk about pods and how they talk together. And that is going to involve a CNI plugin. Kubernetes is not opinionated, right? It doesn't come with a networking solution. It doesn't come with a container runtime. It doesn't come with storage drivers, right? You have to add all those in through the container network interface, the container runtime interface, and the container storage interface, right? Those are the 3 big legs of the Kubernetes stool. It's very rare to find a Kubernetes cluster that doesn't have plugins for all 3 of those, and sometimes multiple plugins for some of them. But to just get up and running after you've installed Kubernetes, you're going to need a container network interface plugin, and we're going to use Cilium. Cilium is a project at the CNCF, really cool solution for networking, and we'll talk about that briefly. Then we're going to get into step 2, which is Kubernetes services. So once we've got our cluster running, and we've got the network in place, and we've seen how it works and understand the absolute basics, we're going to dig into services. And we're going to see how services give us a front end for a set of dynamically changing pods. Clients don't want the heartburn of figuring out who to connect to. They want a virtual IP address that they can look up by name, that they just connect to, and then the magic happens, and they get to one of the pods, right? So that's what services are all about. We're going to look at how Kubernetes does that, at least one of the ways that it does it. And then we're going to take a look at DNS. Humans don't like to remember IP addresses. Also, IP addresses tend to change a lot more than concepts. A service name is a concept. If you have a CFO reporting service, it's probably going to be called CFO reporting forever or for a very long time, and anywhere you put it. But if you deploy that in Singapore, it's going to have one IP. If you deploy that in London, it's going to have another IP. So services use these names to create an abstraction, again, another level of abstraction on top of that virtual IP. And we're going to see how Kubernetes implements DNS, and it does it in some interesting and creative ways. One thing that's fundamental that we're going to hammer on a little bit are concepts around Kubernetes. You'll never understand Kubernetes networking if you don't understand Kubernetes. Kubernetes thinks about the world a certain way. You don't have to deploy applications that way. But if you don't understand it, you're going to keep stepping into potholes. If you understand it, you can protect yourself and say, well, Kubernetes wants this to be this way, but we're going to change it a little bit, and we're going to make sure we've done the correct things to keep Kubernetes happy when we do it slightly differently from how Kubernetes expects. And this really applies to networking, and we're going to see some of this in the DNS section. Next, we're going to do step 4, which is outside access. We're going to see how from a cluster where you've got all your cool services running, you can get from the outside in. And there's a lot of ways to do that, but fundamentally, there's 2 simple paths. And there's lots of other crazy stuff that people are marketing and trying to tell you do all this. There's 2 paths. Under the covers of all these things, there's 2 ways in. And so we're going to look at that, and we're going to talk about some of the cool projects that fit in there. In addition to core DNS on the DNS side, we're going to look at Emissary for ingress and gateway kinds of functions. Envoy is a proxy that Emissary uses under the covers. And then we're going to look at, well, we're going to talk about MetalLB. Sometimes when we do this talk, we run MetalLB, but with this many people, it would be crazy. So we're not going to do that. But we'll talk about it a little bit. And then finally, we're going to get into service mesh, step 5. This is sort of the pinnacle, right? After you've got everything else working perfectly, that's when you might want to start thinking about service mesh. Not everybody needs a service mesh. I don't buy that. Not everybody needs a service mesh. However, a service mesh is an incredibly powerful and valuable thing, and so you might need it. You might want it. It can be an incredibly valuable tool. We're going to talk about what service meshes do, and we're going to use the only graduated project in the CNCF ecosystem that is a service mesh, Linkerd. And it's a super cool project, has a ton of amazing features, and we'll just scratch the surface in this session. But you'll have it installed. You'll see how easy it is to fire up, and you'll know the basics, so you can, again, carry on your journey and explore Linkerd all you want after the fact. OK, so that is our plan. Now let's see how we do. I'm going to quickly switch over here. We have burned 10 minutes. Yikes. OK, we got to get going. All right, so step 1. And remember, if you've got questions, there's 3 guys, right? Chris, Ilian, and Valentin out here that will help you out. So just raise your hand, and they'll come and answer your questions while I keep going to keep us on track. All right, so container networking concepts. Let's talk about this just briefly. The first thing I want to say is there's no such thing as a container. Maybe that's a little shocking in a container-based convention. But there really isn't, right? The Linux kernel has C groups. What do? They are control groups. They control how much memory or CPU you can use. The Linux kernel has namespaces. What do? They isolate what your process can see. Can your process only see itself and its children, or can it see the PIDs of other processes? That's the PID namespace. But what we care about is the network namespace. A network namespace makes it so that a process can have its own virtual copy of the IP stack. Inside what we think of as a container, you have your own route table, your own IP tables, your own interfaces, loopback, and things like that. So that's really useful because now we can reliably deploy things that listen on port 80 many, many times on the same computer because they all have their own interfaces. So this is magic, right? If we had a big cluster of machines and we wanted to dynamically roll out applications, if they were all fighting for ports and craziness like that, that would be pretty tough. So what ends up happening with container tech is you get reliable deployment. That's a really huge thing. But we need something to sort of do the deployment, right, to make the deployment work, and that's where Kubernetes comes in. And Kubernetes there's no such thing as a container. What Kubernetes does is it takes and it runs several of them in the same network namespace. That bundle is called a pod, right? They share the network namespace. They also share the interprocess communications namespace. We want it to be cheap for them to talk to each other, right? So if you're using MQs or shared memory, stuff like that, those are in the IPC namespace. And if you're using the local loopback and stuff like that, that's in the network namespace. So pods are collections of container images that are all running in shared network namespaces. So in Kubernetes, interestingly, the pod is the unit of distribution. It's the smallest thing you can schedule. It's the smallest thing that you can scale, and they're atomic. You can't run part of it on one machine and part of it on another, right? So really what we're thinking about when we move to Kubernetes is not container networking, it's pod networking. And so pod networking works like this. You have an interface in one pod and an interface in another pod. They both have IP addresses, and now you can talk. right? These two guys can communicate with each other. And you can have as many containers as you like in the first pod and as many containers as you like in the second pod, or as few as you like. So pods are the unit of distribution and also the unit of network identity, right? The unit of networking. They have an IP address. Interestingly enough, the pods need to be able to communicate with each other. That's what Kubernetes says. All pods in a Kubernetes cluster must be able to communicate with each other. Right? Now, the world's changing. There's lots of exceptions to the rule. But as far as your basic network requirements for Kubernetes to function the way that it's supposed to, all the pods have to be able to talk to each other. Now, what if I want to put some pods in the staging namespace, and I don't want them talking to pods in the production namespace? Well, you can create network policies that change the rules up and stuff, but it has to be possible for every pod to talk to every other pod. What that means is that pods need to be able to communicate with each other when they're on different machines. Linux has stuff built into it, like Linux Bridge and things like that, that acts like a virtual switch where all the pods can talk to each other, and you don't really need any extra software. But as soon as you start communicating outside of the computer to another computer, something's got to happen, right? Because these pods, in the old days, we might put a piece of software on there, and then we might go and program the network a while, and now everybody knows where it is. That's not going to fly in Kubernetes, right? Where we're deploying 9 times a day, 10 times a day. Pods are scaling up and scaling down all day long. That's not going to fly. It's got to be automated. So we need software-defined networking. But the problem is, if Kubernetes just said, yeah, supply some software-defined networking thing, it wouldn't work because Kubernetes would be integrating with 50,000 different things. And so the CNI is a standard that makes it possible for Kubernetes to make the requests that it wants to make, like, hey, I've started up a pod, and I created a network namespace for it, but it's plain vanilla. There's no interfaces, there's no rules, there's no routes, there's nothing in there. So hey, Mr. Software-Defined Networking thing, please wire this pod up so that it can talk to other pods on this computer and any pod in the entire cluster. So the CNI solutions generally have at least one and sometimes 2 components. The first component is a daemon set pod that runs on every node in the cluster and handles the organization of all the pods on that cluster. And then sometimes there's a control plane too. But those CNI components make it possible for pods to reach each other when they're on different hosts. And they can do that in lots of different ways. They can just use routes, right? You can give every host a subnet, and then the plugins can discover each other's subnets through lots of ways, gossip, or they could use etcd to save all that information. And then once they get an outbound connection, they can say, oh, yeah, that IP address I know is on that host, so I'll just route the traffic. They don't have to encapsulate it or do anything like that. On the other hand, it's nice sometimes to encapsulate the traffic, because if you do, then you can do things like encrypt it on the wire. You can do things like make sure that the underlying network doesn't know that there are pods, right? It just sees 2 hosts talking to each other instead of a bunch of 20 different IP addresses from one computer. If you try that on a cloud provider, they're probably going to kill your traffic. They're going to go, hey, that machine, I know its IP address is .7, and I see all these crazy source IPs coming out of that box. There's an attacker in there trying to spoof, right? And so, of course, you have to go to the cloud provider and change settings to make all this stuff work. If you just don't want to have to worry about that, if you want something that's totally portable and goes from your bare metal environment to your cloud to somewhere else, then an overlay could be better, right? So there's pros and cons to everything. There's no one right answer. But in the case of a lot of these plugins, you have choice. So we're going to talk about Cilium for just a sec, and we're going to use it in the first lab. Cilium is a CNI plugin that gives us options. And it is kind of in the new generation of CNIs that are trying to leverage eBPF. So there's a way to tell the Linux kernel to run little programs, and therefore it's very fast because you don't have a user mode component constantly messing around with the network traffic. And so that's exactly how Cilium works. It uses eBPF, leverages that. And Cilium gives you the ability to use an overlay network. So you can tunnel the traffic between the hosts where the network underneath doesn't see the pod traffic. It just sees hosts talking. Or you can route the traffic. It's up to you. Cilium gives you some flexibility, and it is a really cool CNCF project with a bunch of neat features. So we're going to use that as our CNI plugin, and that's going to give us this. Now, you all have one node, right? We already have like 400 computers stood up, so it would have been 800, and it just keeps going from there. So we're going to do everything on a single node Kubernetes cluster, but it's going to work exactly the same as if you had 100 nodes, and that's the important thing, and that's what Kubernetes and CNI brings to the table anyway. So if you had 2 hosts, for example, the hosts have interfaces and the pods have interfaces, and the CNI is the thing that takes care of making sure the traffic can get back and forth. All right, cool. So we've sort of disambiguated CNI. We've talked about some of the solutions. There's lots of other really cool CNI plugins, by the way. Weave is another one that we use a lot at RxM because it's just super easy to install. Calico is probably one of the most popular ones out there that a lot of people use as well, and the list goes on. So there's many, many options, and they all have different pros and cons. But what we're going to do now is we are going to switch to lab mode. And that link I put in the presentation, again, up here. So you have it on your sheet. You also have it up there, right? And there's a backup link, too, if you, for some reason, can't get to GitHub. I thought the reason we did the backup link is GitHub got flaky for me this morning. And I was like, whoa, you know, somebody attacking GitHub, that would be terrible. And so we put a backup link. But I would just use the GitHub link, because if you do, you're going to get a nice formatted, web page that you can just follow and copy and paste from. Now, one thing I want to mention is in the instructions, it's walking you through all the steps, right? So it says, hey, do this, right? And then it says, hey, do this. But some of these things say, hey, do this, and it's specific to your computer, right? For example, if you create a pod through a deployment, that pod is going to have an IP address that is unique to your setup. Right? And another example here, pinging an IP, right? Anytime you see an IP, you got to ask yourself the question, what IP should I be putting in there? Because it's not the one in the sheet, right? The lab is an example, and then you're going to have to make some interpolations. Usually it'll tell you, right? It says right here, note, there are lots of different machines, use your IP address, that sort of thing. All right, so that's lab step 1. It's going to have you let me just kind of walk through it real quick. You can start right now if you want. So open this document up. You can read this little top section, and then it walks you through SSHing into the lab system, right? It literally explains how to log in to the lab system with SSH if you've never done that before. Here's the link that I was mentioning that can give you SSH help if you need that. And here's the link that shows you how to stand up one of these Ubuntu boxes on your own laptop so you can run the labs later if you want to do that. Right? And so once you've done this, it has you install Kubernetes. We built a really cool little script that does everything except set up the CNI plugin. So we're just going to run that. That's going to take a minute or two, so start that now if you can. And then you're going to see the status of your nodes. You're going to realize you need a CNI plugin. We're going to add Cilium. We're going to play around with it a little bit. Then we're going to poke around under the covers and see how our pods work and how the IP addresses are getting assigned, and really just look at the whole IP space. And then we'll clean up at the end. And so step 2 is services. I will indeed be breaking again for services in a little bit, but if you get to the end of this lab and we're not back into the discussion, keep going, right? Drill into the services. It's okay to get ahead because I'm pretty sure you're going to be behind at some point in this session. So SSH into your lab instance, install Kubernetes, set up CNI, and then explore the pod network. Have fun. Holler if you have questions. And I am, for the people who are virtual and who don't have laptops, I'm going to probably do these steps real quickly on the overhead so you can just see them. All right. Let me look at the time, too. OK, what are we talking about here? So it is 11:23. So this one might take a little bit of time. I'm going to give everybody till, say, 11:30, and then we'll do a check-in. All right. Obviously, you can use any, SSH client you like. I'm up there as well in the keys, and I think it's on the sheet if you need it. Hey, Valentin. Hey, Valentin. Do we have a lot left?
Yeah.
Oh, cool. All right. All right, I just started the Kubernetes install on I'm running the Kubernetes install. It's installing Docker first. We're using Docker. That's the runtime. Why Docker? Docker's a poor choice for production. Not because Docker isn't amazing. Docker is amazing. It's just giant, and it has all sorts of stuff in it that you don't want in your production environment. If you're a developer or if you're experimenting, you want Docker because it's awesome. It has all sorts of cool tools and features and techniques that you can use for debugging and experimenting and exploring. So that's why we use Docker here. We just install Docker, and then we install the Docker shim, which no longer comes with Kubernetes, so you have to do both steps. Docker's getting installed, then the Docker shim's getting installed, then we're going to install Kubernetes latest, which is 1.23. You might also ask, what distribution of Kubernetes are we using? Stream Kubernetes. Plain vanilla, 100% completely compatible, the Kubernetes. And we're using kubeadm to install it, which is the reference installer. It's the node installer that runs underneath like kubespray and stuff like that. So no special gimmicks, the basics. And the stuff we add, which is going to be a lot. Running this script is the thing that takes the longest, so everything else is a lot shorter after. Nothing, so that's not bad. Just a minute or two there. Just look at my node. It's not ready. It's not ready because I don't have a CNI solution. So I'm going to read on in the lab. Lab tells me your node's not ready. Now we're going to install Cilium. This is going to make our node ready. There's 3 steps. So you can see what's happening. We're downloading a tarball, right? That's the first piece. And then once we've got the tarball downloaded, we have to extract it. And that's going to give us the Cilium CLI. So a lot of these, kind of modern projects for Kubernetes use the operator pattern where they actually have maybe a command line tool, and then they run a service in Kubernetes that you can interact with, which is nice because you can get data and things from it. And then that service is responsible for actually deploying the pods that are doing the thing you're trying to do. So I have the Cilium CLI installed now. I got my version information, but there's no Cilium on my cluster. If I go back and do a get node, it's still not ready. So I have to tell Cilium to install the CNI plugin. And that's the last step here before we are up and running. These guys, of course, have all sorts of their output, which is cute. Of course, every time you do one of these things, containers are being downloaded, right? As far as it's possible, when kubeadm installs things anyway, the control plane runs in containers, in pods. So you have the scheduler in a pod, you have the controller manager in a pod, you have the kube proxy in a pod. The node agent, the kubelet, can't run in a pod because it's the thing that creates the pods, but beyond that, everything's in a pod. So now that we've got Cilium up and running, we can do some things like ask it status. All right, this is the nice thing about having a CLI and a control plane. We get all sorts of pretty colors, and so it looks good, right? We have the operator running, and we have a single node, so we have a single Cilium, agent running. If we were running, 40 nodes, because it's a daemon set, it would run on every single node, and there'd be 40 of them. But we only have one node, so we only have one of the Cilium plugins. All right. It just has you look around and explore the network a little bit. Make sure traffic is going back and forth. Has us run a little pod and verify that we can get to it. Let me do that real quick. Use the kubectl run command, which manifests behind the scenes and applies it to the cluster. So this one's going to create a pod called web with the image HTTPD and defaults for everything else. And output wide and kubectl get pod is going to show us the IP of the pod. And that way we can test it. All right. Thank you. Some moderation goes on. We get a chance to take a look at the Cilium config, and I'll just run a couple more of these commands. So this is the pool of IP addresses that's going to be handed out to our pods. The lab kind of walks you through the different pools, right? We have the internet, where everything goes except some reserved address ranges. Then you have your cloud host machines, which are probably using one of those reserved ranges. And then you have the pod network, which is inside that cloud. And so these things all need to not conflict, right? You don't want to conflict with the public IP address because they might need to reach you or vice versa. You could proxy them, but and you don't want to conflict with the host IPs. That would be confusing. And then the pod IP space is also going to need to be unique. When you set up your cluster, you can specify, but it's the CNI that decides what IP address your pod gets. That's why it's set up here in the CNI function. So if you wanted a different range, you'd have to tell Cilium when you installed it. And if you do a Cilium install -- help, it'll dump out a gajillion options that you can use. And there's also a config that you can set and apply in kind of a more infrastructure as code approach. All right, and so we work out, do a couple more things, and then finally we clean up at the end. I didn't actually create the client, but I'm going to go ahead and just delete the web guy and call it a day here. Step one done for me. You just do a quick show of hands. If you're still working, great. How many people have finished with step one, though? Okay, great. Let's move on. If you're still working, that's great. Don't feel slow. You're probably going really fast, actually. But we're going to try to keep on the clock here. So give me half an ear while you keep working if you want to. This is a tutorial. It's all about the hands-on. So if you have a choice between ignoring me and doing the lab and not ignoring me, I would ignore me. So Kubernetes service communications. Let's take a look at how Kubernetes thinks about services. When you are running pods, let's think about Kubernetes 1.0. Kubernetes 1.0 was for microservices, period. End of story. There were no no real provisions for any kind of stateful workloads. Cassandra is not a microservice, right? It is a clustered storage engine where you run many, many nodes, and it's horizontally scalable, and it's absolutely a cloud-friendly kind of data store. But it's not a microservice. Microservices are stateless. State is hard. Scaling your Cassandra cluster, sizing it, doing all those things is hard. But running a microservice is easy. And destroying it when you have 7 others shouldn't ripple the waters at all. Nobody should care. You get disconnected, you reconnect, and you end up with one of the other guys, and they're all the same. That's what microservices are all about. And so Kubernetes embraces this. And so we can run a whole bunch of copies of our service under a deployment in Kubernetes, and then to avoid customers having to worry about the mayhem of pods scaling up and down and getting deleted because a node is overloaded or whatever, we put a service in front of it. And that service has a head, a cluster IP, a virtual IP address. It's not associated with any interface. It's just an IP. And when you try to connect to it, the Linux kernel has to figure out what to do, because that address isn't associated with anything. There's nowhere to send the packets, right? And so Kubernetes implements the routing functionality, the forwarding functionality that makes that all work. When you create a service, you get a cluster IP, and you get the wiring that delivers your connection to one of those back-end pods. So how do we make that go? Well, there's a thing called the kube proxy. It runs in a pod as a daemon set on every node in the cluster, and it's doing that stuff. Its job is, every time a service is created, so it's watching the API service saying, hey, tell me about any services. And when a service gets created, it immediately goes and tells the Linux kernel, do all this stuff, right? And now all of a sudden, people can reach those pods through those services. And when pods come and go, the kube proxy is watching that too. If a pod goes away, he takes that pod out of the mesh. If a pod shows up and has the right label, he adds that pod into the mesh. So the kube proxy is the magic. Now, how does the kube proxy make this work? Well, the slowest way is it can do user mode. But this is deprecated, and this was used in the early beta days of Kubernetes, where the traffic would literally connect to the proxy, and then the proxy would make the connection outbound for you. So that's no good, because now you got a user mode process, and your data path is going to be slow. So the next thing we can do is use IP tables. We just tell the kernel, hey, when somebody connects to this IP address, use a destination network address translation to one of these pods. And a lot of people don't know it, but you can randomly select a rule in a chain of rules in IP tables, and that's what's happening, right? So if there's 20 services back there, it's just going to randomly select one of them and then send you to that guy. So it's load balancing, right? It's random, but it's load balancing. And if pods are coming and going like crazy, and one of the pods gets overloaded, that pod's likely to be evicted, and all those connections are going to break, and they're going to redistribute immediately because the clients are going to reconnect. If you're talking to a microservice, you should expect it to be ephemeral, right? Note to people writing client code, expect that connection to break. Don't be surprised by it. When it does, you just reconnect, and you're going to get distributed to somebody else. So the entropy of the cluster naturally distributes the load pretty darn well. A lot of people are like, let's use some sophisticated global rate limit, blah, blah, blah. And at the end of the day, try it. Try the simple stuff first. It's often fastest, right? But if that doesn't work for you, there's other options. Now, one thing that probably is an upgrade is IPVS. So the kernel has also another mechanism, IP virtual services, and it's a teeny bit faster than IP tables in some situations, and a lot faster in some others, because it uses a lot less resources. That's the main thing. IP tables were never meant to be distributing traffic. So IPVS is probably the better option. You can tell kube proxy which of these modes you want to use, and the default is IP tables. So that's the one that we're using in our lab, because we didn't tell it to do anything else, right? There are also CNI plugins that have fancy features too, because eBPF, hey, programming the kernel sounds like that would be a way to handle these services too, right? Well, it is, and it has some benefits. So some of the plugins let you do that. You could replace the kube proxy with Cilium if you wanted to, and let it do all that stuff. We didn't tell it to do that, again, so it didn't, but that's an option that's on the table. Now remember that all of the hosts in your cloud, virtual private cloud, right, have to have unique addresses if they're going to talk to each other. So all your Kubernetes cluster nodes have to have unique addresses. And then all of the pods that run in them have to have unique addresses. And since you need to be able to get to the pods from the host in order to, do things like check their health and stuff, those addresses have to be unique, right? Non-overlapping. And then the last thing is these service IPs need to be unique and non-overlapping. So we have 3 address spaces we got to think about when we're setting up Kubernetes. This is part of the architecting a cluster process, right? What are the address ranges we're going to use for these things? And another interesting thing is the support for IPv4 and IPv6. We're doing everything in IPv4 for no reason. It's just what happens by default, right? This is the way things work by default. But out there on the internet, IPv6 continues to gain steam. A lot of companies, especially telcos, are IPv6 internally everywhere. And so there's a good momentum towards IPv6. In Kubernetes 1.0, it was IPv4. That was the end of the story. Next, IPv6 only went GA in 1.18, right? That was a long time later. And you had one or the other, right? No, not both. You could pick one, right? And this is as far as what Kubernetes is responsible for, so the cluster IPs, right? If you had a CNI plugin that knew how to do IPv6, well, knock yourself out. That's fine. But the services are always going to be IPv4 or IPv6 until 1.20, where we got either IPv4 or IPv6 in the same cluster. Right? Now you could pick. You could have an IPv4 service over here and an IPv6 over here. Pretty cool. But you still couldn't have a dual stack service, right? That was out of bounds until, 1, 2, 3. 3 weeks ago or whatever it was, we now have GA, IPv4, IPv6 dual stack. So you can pick on a cluster to make a service single stack. You can make it prefer dual stack, and then you can require dual stack. And that means that the users got to have both, right? So those are pretty cool features. The Kubernetes project is really stunning how fast it moves and how much tech is in it when you look at all the different places and how advanced it is. So some things are a long time coming. That maybe was, but hey, it's here now. Services. How do we create one? Well, in Kubernetes, you pretty much create everything by specifying it and giving the specification to Kubernetes, and then Kubernetes just spends the rest of its life trying to make the status of the cluster the same as your specifications. That's what Kubernetes does. It makes the status of the cluster the same as your specifications. That way, you don't have to constantly get up in the middle of the night and say, oh, that pod stopped, let me restart it. No, you said, I want a pod running, and if it stops, Kubernetes restarts it. Self-healing, all these types of, automate the toil, SRE stuff. So this is a service. It's a very simple one. It has a name, web. It has a port, 80. The port has a name too. And in case you have multiple ports, you can use SRV records in DNS to discover which ones are which and stuff. And then we have a selector that says, hey, any pod that has the label key app value web gets this traffic. Right? So if there's 100 of them, you'll have 100 of those pods getting connections when this service is hit. If there's one of them, then that one will get it. If there's none, then you can't connect. There's no such thing as a virtual IP, right? It's virtual. It's just rules in a table or something like that. So if there aren't any pods, you're not going to go any further. All right. So that's the idea behind a service. Now, all of the pods that match that selector create something called an endpoint. Right? The service could push all the pod information that match the service down to all the kube proxies. But that'd be very expensive because you can have clusters with thousands and thousands of pods, right? And so what's better is to just create a little thing that has the IP address, and that's about it, right? An endpoint that identifies the targets that you want, and then you send those down to the kube proxy. So earlier I said, hey, the kube proxy is watching the pods. It's actually looking for endpoints, right? And so the service controller is creating the endpoints, and then the kube proxy is getting those. So an endpoint looks like this up here. What happens if you create a service that has no selector? That service will never, ever identify any pods to send traffic to. So you're going to have to do it. And this is something that you might do in a scenario where those pods aren't pods. What if you have 16 VMs? And every once in a while, some of them shut down and some new ones stand up. You could create your own glue to create these endpoints. And because the endpoint is named website, we know it's a sub-resource of the service website. And then it's got an address and the ports, just like we had before defined on the service side. And then next thing you know, you look at the endpoints for your service, and this guy shows up if you apply that endpoint. So you can create your own endpoints. You can have them produced dynamically by Kubernetes. So in general, if you're routing to pods, you would want them dynamically created. Now, what kinds of services do we have to work with? There's a bunch. The first kind is a headless service. A headless service has no cluster IP. You literally say cluster IP none. It actually turns out it's a cluster IP type of service with no cluster IP. I don't know how that works, but anyway, you define a headless service by creating a cluster IP service with no cluster IP. What is that good for? It's good for situations where the pods aren't the same. What if one of your pods is a Kafka pod and it has the topic NASDAQ? And what if the other of your pods is a Kafka pod and it has on it the topic New York Stock Exchange? And another pod has life, and so on, right? Well, you can't connect to the life pod if you want to get the New York Stock Exchange data. They have identity, these pods. They're not microservices. So anytime you have a situation where they're not microservices, but you want DNS resolution and stuff like that, this is the kind of service you want. Next, cluster IP. Cluster IP is for microservices, right, where it just sends the traffic. That's the first example we looked at. Node port is another one where if packets are coming in from the outside world and we want them to be delivered to our service, we can use a port on every node, on every host in the cluster, and have that port forward to our service. So that port is reserved for us in the entire cluster. So obviously the control plane needs to know what port range you want to use, and it needs to be in control of which ports are handed out and so on. So we'll look at node port a little bit more later. Load balancer is like node port, except it also stands up an external load balancer. This requires a plugin, right? We have to have some sort of external thing like an Azure load balancer or a Google Cloud network load balancer or something, to interact with, or Metal LB, as we were looking at earlier. And then lastly, we have external name. This is for scenarios where you have a service name that you want to be resolvable inside your cluster. And we're going to look at DNS more in the next module, but you actually want it to look for some name that's outside your cluster, right? So you're going to make a name mapping, and you can do that with external name. All right, so lab step 2. We're going to create a deployment, which is going to have several pods. We're going to create a cluster IP service. We're going to connect to the service, see the traffic reach the deployment, and come back. And then we're going to figure out how it works. We're going to get under the covers, look at the IP tables, poke around a little bit, and see how things are happening. OK, so we are looking at 11:47. How is that possible? OK, let's give everybody, say, 8 minutes. We'll come back at 55 minutes after. Nothing to install in this session, but there is a lot of stuff to look at. So 11:55, and we will be coming back. OK, so I'm going to go ahead and do this second step, and I'll talk through it. But for the people locally, you can just ignore me and work on the lab yourself. So first thing we're going to do is we need some pods to connect to. So we're going to create a deployment with 3 replicas, and it's just going to run the Apache web server. So we do that. OK, cool. If I can type. All right, good. We got our 3 pods up and running. Head and show the labels on these pods. And when you create a deployment using that imperative technique, that's just quick and dirty, right? Normally you'd create a manifest, but when you use that technique, you're going to get a label, key, app, and a value, which is the name of the deployment. So I can predict that, right? I know I'm going to have this app website label. I don't know what the name of the pod's going to be because they're ephemeral. They come and go, and they're identityless, right? I shouldn't care about the name, but I know that they're part of this website, package. All right, so the next thing I want to do is I want to create a cluster IP service, and we're going to do this. This is basically the exact same slides. All right, drop that in there. All right. kubectl get all doesn't get everything, but it gets most of the stuff you care about. So I got my 3 pods set for me, and then I've got my service website, and it has a cluster IP. So that was handed to me by Kubernetes. Kubernetes decides what that's going to be because Kubernetes has the service controller, and it also knows what the range of addresses that you want to use are. Now, if we had used kubeadm with the config file or given it the right command line parameters, we could have changed that to use something else if we wanted to. All right, so I'm going to curl that, and it works, but I have no idea which pod I hit. And I don't care. They're all the same. They're replicas. That's the point. All right, so there's some other good stuff in here. And then the next thing that we're going to do is we're going to look for the range that Kubernetes is using. So this is that service controller IP range, right? That's where the IP addresses are coming from for these services. So it's a 1096/12 is what the default is. You could change it. Okay, a little bit more poking around, and now we're going to look at some endpoints. So let's take a look at the endpoints for the website. And we can see there's 3 of them, right? 1015, 10154, and 1054. And remember, they're always going to have the same, first 3 octets because the hosts are subnetted at 24 bits, and then the overall space is 8 bits. We saw that in CNI. So these are CNI controlled, right, by Cilium, and then the service IP, the cluster IP, is controlled by Kubernetes because it's the service controller piece. All right, good. Let's see what else we got here. So the next thing we're going to do is try to figure out how this all works. So we're going to look into the IP tables, and we're going to look for the cluster IP. Obviously, I can't use the one from the lab. I have to use the one that I got, which is potentially very different. Service IPs aren't doled out. See the next one would be, and that leaves you open to some security issues, so they're randomly selected from the range. All right, so I can see that there's an IP tables rule that says if TCP traffic comes from anywhere and goes to that address on TCP port 80, use that chain to figure out what happens. So the next thing I need to do is I need to update my grep to look at the chain called this. And actually, yeah, there we go. And so that our service, and you can see here, this guy says, all right, destination IP 8. Let's run this guy here. There we go. And so those are the 3 pods that we get the packet counts. You can, of course, tell which one you hit when you did your curl, right? It's this bottom guy, as it turns out. So it's just a random probability, 33% when there's 3 of them, 50% when there's 2 of them, and then the last one's the default. And so this is the guy that got hit. And so if I look for the pod that's 10.0.0.54, and I look at that guy's log. So this is 54 down here. So let's look at the logs of this guy. We'll see a bunch of stuff, but there's the hit, right? That was our curl. And then if we do the same thing and look at logs for anybody with the label app website, oh, wow. Go. There are no hits anywhere in here except this one from our curl. So all 3 of the other pods, right? This guy, no hits. This guy, no hits. This guy got a hit. So the service is working, right? Our IP tables are solving the problem of randomly distributing traffic to our pods on the back end. There's a little bit more exploration that goes on there. But that brings us down to the bottom section where we get to delete some things and see how stuff works. So, for example, I'm just going to pick one of these guys at random and delete it. It keeps working, and you never even see any hesitation. And the reason is that the service proxy has taken the deleted pod out of the mesh. And of course, what also happens is that Kubernetes immediately realizes that there aren't 3 pods anymore. And since the replica set and the deployment were set to have 3, it creates a brand new one. It's not the same pod, right? That guy, if you look at the IP, not the same pod, right? This guy is 134, and he's been running for 31 seconds versus the other guys, which are 7 minutes. So the mesh is dynamic, right? It's taking advantage of this dynamic environment and automatically updating all of the routing or forwarding necessary to make things go. All right, so let's move on. And keep in mind, if you're done with 2 before I move on, feel free to move on yourself. All right, so Kubernetes DNS. Let's talk about DNS briefly and how Kubernetes implements it. If you're still working on Lab 2, keep working. Just lend me half an ear. So DNS and Kubernetes. There are 3 files that your containers get that come from the container runtime, not from your image, your container image. They're always overlaid by the container runtime. And the reason is, if you take a HTTP container and you run it in Singapore, it's going to get 1 IP. If you run it in London, it's going to get another IP. So how could you possibly create an etc hosts file with the correct information, right? Since it should have your IP and your host name in there. How could you possibly create a host name file with the correct information, since the name of your host when you're a pod is the name of your pod, and that's dynamically being created, so you don't even know what it's going to be. And then the final thing is resolve.conf. Every Kubernetes cluster runs core DNS by default. Some distros change it and use something else, and some distros configure core DNS in different ways. But there is a DNS server built into Kubernetes, and when you use the reference installer, kubeadm, you get core DNS, which is another CNCF project, one of the earliest ones. And so core DNS will automatically resolve service names inside your cluster to their virtual IPs, so that you can just use names instead of IPs, which is great. But that means those 3 files have to be correctly configured. And so it's the kubelet that understands your Kubernetes environment and sets these files up so that your pod works. And so you have core DNS running in the kube system namespace. As you can see up here, we have 2 pods, core DNS pods. So if one of them crashes, we have resilience, right? Kubernetes eats its own dog food. Core DNS runs in a deployment. And then there's a service also that gives us a cluster IP for DNS inside Kubernetes, and it's 10.96.0.10. That's the default IP for DNS, and it's going to be injected into every single pod in resolve.conf. Because when your pod tries to look up a name, it needs to go to core DNS to find the IP of that service. Right? We don't generally look at pods. Right? They're ephemeral. We don't care about them. We care about the API that we're trying to consume, right? The interface, not the implementation. And so that's a quick look at core DNS and how it's set up and what it does. And then if you want to think about DNS inside a cluster, number 1, you might have many clusters. So you can give every single cluster its own suffix, right? Cluster.local is the default, and so you get cluster.local in the example we're going to look at. Next, there's the service bucket where services live. There's some other buckets, but this is the most important one. And then namespaces are a thing in Kubernetes, right? If I want dev and production, if I want team A and team B, if I want blue, green, whatever, different namespaces are isolated from each other. And so if you create a service called Fred and I try to create one and I get an error, that's going to be confusing, right? If we're in completely different departments and contexts and we don't even normally talk to each other, that's going to be a big problem. So namespaces give you the ability to create any name you want, which means the DNS has to be isolated. And so the namespace is in the DNS name. And then finally, you have the name of the service itself. So an example of a realistic production DNS name for a service in Kubernetes might be web, if your service is called web, production, if your namespace is called production, .svc, and then kates54.rx-m.com if that's the suffix you gave that cluster. And so you can see with this kind of a unique name, I could actually reach a service in a completely different cluster. Right? I could give the name of the service, the namespace in the cluster, the SVC, and then the cluster suffix. And as long as my networking, normal, computer networking infrastructure knows how to deliver that packet to that cluster, we've got connectivity. So headless services are another thing. We mentioned if you say cluster IP none, you'll get a headless service. Well, what happens in a headless service? In a headless service, you don't want the cluster IP. You don't want to look that up because it's no good, right? You don't want to randomly go somewhere. If I want New York data, I have to talk to that Kafka node. If I want life data, I got to talk to that Kafka node. So in a headless service, you get the actual IPs of all of the nodes or all the pods when you look up the service name. So it's not just one IP of the head of the cluster IP. You're going to get all the pod IPs together. The other thing that is important is that there's a special controller for stateful pods called a stateful set. And it creates pods with deterministic names, with identity, with persistent identity. If this pod, which is, let's call it Web 7, gets evicted from a computer, we won't get Web 58 over here, we'll get Web 7 again over here. It might have a different IP, but the name will be the same. So if you create a stateful set of Redis, the pods will be called Redis 0, Redis 1, Redis 2 with an ordinal as they get created. So you can predict the name, and that name will be persistent. It won't go away. In other words, the Kafka guy that's servicing the NASDAQ market data, when it crashes, it's going to fire back up over here, and it's going to still be Kafka 7 with the NASDAQ data. And the volume it was using is going to chase it if it's network attachable. So that's what we want in a stateful set. And so if I need to look up Kafka 7, I don't want to fix myself on the IP. What if he gets punted to a new machine and gets a different IP? I want to use the DNS name, right? I want to be abstract from the machinery of the networking. And so I could say, hey, redis1.redis.dataNS, which is my namespace, service cluster local. Let's say that's the guy who has the NASDAQ data. Then I would just connect to that guy every time. And I would always get the NASDAQ data. So that's what a headless service brings to the table. It creates this DNS structure for stateful pods. And generally, that's why you use a headless service when you have stateful pods. And so overriding the DNS is also possible. What if you're an administrator and you have to run a pod, and that pod needs to talk to an external DNS system? You don't want it going to the internal one. You want it going to the external one. You can set up your resolve.conf as custom as you like. A resolve.conf is generally going to have a name server to connect to, searches, so suffixes that you would add, right? If I look for web, it's going to work. Why? Because there's a suffix in there that is going to specify my namespace .service. Whatever my cluster suffix is. I can just look up the service and it works. If I want to look up a service in another namespace, I can just say service.other namespace and it will work because there's multiple search paths, right, for each piece of the DNS name. And then finally, you have options that you can set. So this is, if you're not a DNS guru, you can ignore this. But basically, these are the ways that you can override what's in the resolve.conf. So step 3, playing around with DNS. Let's give everybody, let's say, until 10 after to work through that. Seven minutes. Again, go ahead and work on your own. I'm just going to laptop. I'll just give you a preview here. So let's see. Did I clean up after myself last time? I did not. Let me go ahead and do that. So I'm going to kubectl delete some stuff real quick. All right, so on the DNS side, we're going to create a deployment again. And then we're going to expose it. This is a cheeky way to create a service. Right? It creates a service that's wired to that deployment, so it figures out what labels to use automatically. And now I'm going to run a client, and we're going to look around at how we can resolve the name instead of the IP. So BusyBox image has to download. We'll let it do that. And the idea is, let's just try first to there's no curl in BusyBox, so we'll wget the website. And this is DNS, right? I'm saying, hey, look up website. I mean, how does that work, right? How does that work? It works, but how does it work? Well, let's take a look at the DNS machinery. Right? The first thing that we would want to do is look at the resolve.conf. Right? Whenever your resolver, the part of the Linux library or the glibc or whatever it is that's doing your resolution, it's probably going to a cache. If it doesn't see the name there, then it's looking in your etc hosts. If it doesn't see the name there, then it's going to DNS. So where does it find the DNS server? Well, there you go, myresolve.conf. Recognize that IP. It's 10.96.0.1. That's our core DNS service. It's the cluster IP of our core DNS. Kubernetes eats its own dog food. Then look at the search suffixes. I'm in the default namespace on cluster.local. So when you make the name, right, if you fully qualify it, and you say .default .service .cluster.local, right, that's what's happening, right? We're just adding that search suffix, and it's a fully qualified name. It won't conflict with website services in other namespaces. What if I want to get to a website service in another namespace? Well, you can, right? You can simply say website .prod, let's say. Now, that's not going to work because I don't have a prod namespace, but you can see it doesn't work, right? It would have worked if it was in default, but you said go look in prod, and there isn't one there. And so notice that this guy was resolving with service.cluster.local, the second search, right, suffix. And then we have cluster.local, and then whatever gets inherited from the host machines. All right, cool. So we now have the idea of like how the pod side of it's working, right? And I'm just going to exit out of this guy. And if we do a kubectl get all in the namespace kube system, there's the machinery, right? In kube system, we have the core DNS deployment with 2 pods. And we have our replica set, and we have the 2 pods up there. And then there's the core DNS service. So those are the pieces of the puzzle. All right, and the lab goes on, and it has you play around a little bit with some of this stuff. Then it has you create a headless service. A couple minutes, I might do that real quick. So I'm going to go ahead and create this headless service. The special thing about the headless service over a normal service is that it has no cluster IP. And so you can see at the bottom here, cluster IP none. All right. And then the lab has us take a look at the cluster IP service. We see that he's got no cluster IP. And then we're going to jump back into that pod, and we're going to do some NS lookups to see what kind of DNS trouble we can get into. So I'm going to kubectl attach my input stream to, what was it called, client. There we go. Go ahead and try that NS lookup on headless website that we just created. And you can see I don't get back a single IP, I get back all of them. There's 3 pods, I get all 3 of them. And some DNS errors, but you get the idea, right? So we did it, the lookup worked, we got the 3 pods, and you can see that these 3 pods, they don't have unique identity. They're created by a deployment, they have random names, and so we just, hey, here are the IP addresses, if you want to connect to one, you can. But the idea then is to take this to the next level, where we put the headless service on top of a stateful set. So that's this guy down here. Note that a YAML file can have multiple YAML documents. And that's exactly what's going on in here. We have the first part is our service, right? So that's just the service without the cluster IP, right? The headless service. And then this is the stateful set. We're saying, hey, we're going to pretend that these Nginx guys are actually stateful. They're not, but it's all right. And now let's kubectl apply -f, that guy. Now what we have the, we've got this new stateful set called web state, right? And that web state has created a pod, web state 0. So the pod gets the name of the stateful set plus an ordinal, and if I kubectl scale, stateful set replicas equal 3. You got to spell it right. Fortunately, there's a shortcut. All right, so that's 0, 1, and 2. So if we go back up and attach again to our previous guy, and then we ns look up web state. Let's just do that. You can see that we get the lookup, as always, right? Web state is, in fact, a service. But now what we can do is we can ask for a different kind of query. We can ask for an SRV query. Is it equal? And you can see that over here, web state 0, 1, and 2. So we can identify these guys now by their actual names. And if we try to, for example, curl a specific one of them, we could say web state. I want to talk to specifically the NASDAQ guy, right? Because I don't want the New York Stock Exchange data. I want the NASDAQ guy, and he's number 1. And curl's not found, so I'll use wget. And then, right, we hit the Nginx guy there. So that's DNS in its various flavors in Kubernetes, right? And of course, I mean, as you guys know, there's a lot more to know, but the lab does start you down the road. Hopefully, is pulling away the veil on some of the more confusing bits and the things that aren't obvious when you start off. All right, so let's move into our next section: accessing services from the outside. How do we get from the outside in? Keep working on the labs if you want. Let me in here. So outside access can be performed in lots of ways. At the end of the day, there's host port and node port and a lot of stuff on top of them. Host port and node port handle 99.99% of the traffic flowing into a cluster, one of those two techniques. So what does a host port do? It's not a service. In a pod, you can say, take this port on the host and map it to the pod's listening port, right? And that will work. The problem with that is it's not very friendly to the cluster, right? If you want to map port 80 on the host, I mean, good luck. What if none of the hosts have port 80 open? Your pod can't run anywhere. So it's not a great solution for users, for us developers who are trying to deploy apps, right? You don't want to use a host port. It's for administrators, right? If I'm running, SSH in a pod, well, yeah, I want it to listen on 22, so I might host port that or something for diagnostics or testing. But it's not for general use for users, right? What users should be using is a node port. A node port's a service, and it's a cluster IP. You get a cluster IP, right? It's like an inheritance hierarchy, right? Cluster IP is the base class, and node port is a derived class. All the cluster IP stuff you get, plus a port is selected from the node port range, like let's say 310, right? 30010, so 30,010, I guess. And that's your port. And every single host computer will now take traffic on that port and forward it to your service. So if you set up, for example, a load balancer in front of all the nodes in your cluster and direct traffic to that port, you will be reaching your service. And that's exactly what a load balancer service does. So the inheritance hierarchy continues. Cluster IP, node port, load balancer. The load balancer is the most derived, right? It is a node port, and it is a cluster IP. So inside the cluster, you can use the cluster IP. That's best. It's DNS resolvable. It's going to load balance you. It's fast. Then node port, that's one hop, right? You go right to the pod. Node port is 2 hops, right? Because you have to first hit the port on the host, and somebody's got to forward your traffic to the next hop, right? There are scenarios where you can have actually a user mode proxy, like kube proxy, and some versions of Kubernetes will actually listen on all the node ports and forward the traffic. In other cases, it's handled by the kernel, the eBPF and stuff like that. But then ultimately, your traffic ends up being delivered to the pod, and the pod's probably not on that computer, right? Unless you know specifically, if there's 100 computers in the cluster and you're running 5 pods, you're only running on 5% of the nodes. If you pick a host and hit the node port, chances are your pod's not on that node. So you're going to have 2 hops, right? You're going to hit the host, and then it's going to have to forward your traffic over to the machine that has the pod, right? And then load balancer, 3 hops. The load balancer, there's no load balancers built into Kubernetes. You have to have a plugin that stands one up for you. So MetalLB can be stood up and use BGP to advertise a virtual IP that goes to the node port or something like that. You can also use things like, the load balancers for your cloud providers, and F5 has one. There's all sorts of load balancers out there that will plug in, but you got to do it, right? Kubernetes is not opinionated. You pick your load balancer, and then when you set up your service, it creates the event, and then if somebody wants to do something with it, they can. In our cluster, when you create a load balancer, it's going to be pending. You're never going to get the external IP of the load balancer because there's no plugin installed. And so load balancer is 3 hops. You hit the load balancer, which is a thing, a real device or a logical thing, right? And then it hits the node port on one of the machines, and then 3rd hop is back to the pod. So it's a hierarchy, and each one's more expensive. So you got to decide what you want to do. Load balancers are nice because you can give them a DNS name out on the internet, for example, and you might have a hardware replication of them. There might be like 7 of them, so if one fails, HA and all that. So load balancers are good for external access too, but they're based on node ports typically. They get into the cluster through a node port. And then you have ingress. An ingress is a controller that runs in your cluster, typically has a load balancer or a node port service in front of it. But the thing about an ingress controller is, what if I have 5 services? Do you want to tell your iPhone developers, oh, if you want that, you connect over to here, and if you want that, you connect over to here, and then, oh, this part of the API is actually hosted over here? Not really, right? Microservices shouldn't be exposed outside of the context within which you're developing them. The external API deals with different language, different semantics, different bandwidths, right? The internet is flaky and low bandwidth. Your data center is going to be fast and reliable. They're very different worlds. The ingress controller can create kind of like a firewall, an adapter from the outside world to the inside world. You could have 2 services or 8, and then you could say, hey, if somebody hits /engine, send them over here. If they hit /web, send them over there. And so an ingress controller gets rules that tell it how to send the traffic inside the cluster to the different services that are on the inside. So you might have a bunch of your little microservices with cluster IPs only. You don't want them accessed from the outside. And then you have an ingress controller that provides your public interface, and it sends all the traffic to those guys behind the scenes. And it's the ingress controller that has a load balancer service in front of it, and only the ingress controller. It's the one way in. Right? So you might create node ports on the fly to test things and to experiment if you're on the inside, but the outside world never sees those. What's a gateway? A gateway is a more powerful ingress controller. Ingress is a thing in Kubernetes. It's a defined framework. Again, Kubernetes doesn't provide one. You have to install one. And we're going to use Emissary. It used to be called Ambassador. And so we're going to use Emissary for that. Well, guess what? Emissary does the Kubernetes ingress framework, but Emissary is crazy powerful and has tons of other features. It can inject headers. It can do fault stuff for chaos operations. It can do all sorts of things. And so it's a gateway. It's a super powerful way to provide a single place where all your traffic can come in. It can do security stuff. Obviously, TLS is even part of ingress, but it can do some more advanced security things. So it's a very, very powerful tool. All right, so this is an example of host port, right, where you have host port in the pod spec and then the container port. And if there's no host with that port open, your pod's pending forever until that port is available somewhere, right? So not a great thing for developers or users, more for operators. That's a node port. You just ask for type node port, and then you can ask for the port that you want, but if it's in use, you'll get an error. If you leave the node port off, Kubernetes will assign you one from the range, just like with the cluster IP as we saw. And then this is a load balancer, right? You just say type load balancer. That's it, right? In this case, this guy has 2 ports, right? HTTP and HTTPS, which is kind of common. And then you've got ingress. This is an ingress rule. This ingress rule says, hey, if somebody hits the ingress controller using the HTTP protocol, and by the way, ingress only supports HTTP and HTTPS, and they are using the route/engine as their prefix, could be anything after that, then send them to the backend service called engine. That's the name of the service, DNS resolved, on port 80. Right? Very simple. And the developers can create these rules. My DevOps team can provide the deployment that runs my pods, the service that lets people inside the cluster get to them, and the ingress rule that allows traffic from the outside to route in. Now, obviously, I got to coordinate with the other people so we don't have overlapping routes and stuff, but that's the idea, right? Let those teams be independent. And then the last thing is the gateway. This is an example of configuring a gateway. That's a custom resource definition. It's not part of Kubernetes, but Kubernetes gives you the ability to create your own resource definitions like this one. And this one gives you the ability then to do things like inject headers and fancy stuff like control the maximum connections. None of that's supported in ingress, but emissary is super powerful and has all these kind of advanced features, so we would call it typically a gateway. It also supports protocols that the ingress controller doesn't support. Ingress, only HTTP and HTTPS. If you want SCTP or UDP, you're going to need a gateway. And so lab step 4 walks you through installing emissary and doing some ingress and some gateway stuff. So you get a chance to work with the CRDs that emissary installs and the ingress controller standard Kubernetes stuff. Why would you use ingress if gateways are so much more powerful? Well, those specs I just showed you, those custom resource definitions are emissary custom resource definitions. If you later switch to something else, they're not going to work. But ingress is a Kubernetes framework standard. It's going to work everywhere. The Nginx ingress controller will take them. The emissary will take them. So if you can get away with just using ingress, it's portable, right? Not a bad thing. So you have to decide what you need. All right, what I'm going to do is cover service mesh, because we got a little bit of time left. If you want to start on the emissary lab, go for it. But I'm going to cover service mesh real quick. And I tell you what, we'll leave these boxes up for another hour or two. So if you didn't get through all the labs, you'll have some time there. And then probably like after lunch, we'll shut them down, let's say that way. So if you want to work through lunch, you can. So let's hit the service mesh stuff. Service mesh functionality. I mean, we've got all this functionality built into Kubernetes. We've got the CNI, we've got services, we've got ingress, and now these gateways, and there's just so much power and capability from a networking standpoint. And there is complexity, but when you start poking around and looking at it in the labs here, you realize that it's manageable. But what's left, right? Well, if you're a developer and your boss is hammering on you about security, 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 do you really want to go back and instrument every single service you wrote with mutual TLS? And how likely are you to get that right? Anyway, right? And then now you got another thing to debug and to manage, right? That alone right there is a killer, right? And then as soon as you do it, now all your customers are broken. They got to implement, on their side, the mutual TLS stuff. That's a pain, in Java or C++ or Go or Rust or whatever. Well, wouldn't it be amazing if you could just flip a switch and inject a proxy into every pod that did the mutual TLS automatically for every single outbound connection, and on the other side for everything that comes in? That would be amazing. And wouldn't it be amazing if those pods, so that you didn't have to, reported telemetry that says, I'm connecting at this moment in time, I've been connected for this period of time, ooh, I'm seeing these errors come back, and just reported that all to a central repository that you could open up in Prometheus and chart and look at and set alerts on? That would be amazing. And that's why service meshes are amazing. Those are the things that they do. They give you MTLS for free, communication metrics for free, communication policy. You can't talk to that guy, but you can talk to this guy. And you can't talk to that guy on Friday, or whatever, policy. Traces, fault injection, chaos support, advanced traffic management. This is what service mesh brings to the table. And there are a bunch of them to choose from. There are proxy-based service meshes. So this is the long-standing group, right? Your Linkerd's and Istios and open service meshes and so on and so forth. And so those guys are well understood. They're also nice because they operate in the pod sphere. They're not messing around in the kernel or down at the host level. And this means that the second your traffic leaves your pod, it's encrypted. And so that's nice, right? If you're running some sensitive workloads, who are the administrators on those computers, right? So there's some really nice things about having a proxy-based solution. And then the other thing that's also nice about that is that it's not in your software. You can upgrade the proxy without messing with your software, right? They have different life cycles and stuff. Then you have eBPF-based. So this is a little bit bleeding edge. There's some really awesome stuff in the hopper there, but there's some downsides too. And the biggest thing is that I don't think you're going to see a lot of GA eBPF service mesh implementations at this moment. Soon, but it's a little early days there. Cilium, for example, and others can provide that kind of functionality. And then library-based. What if you're using gRPC everywhere? Well, gRPC could do the TLS for you in its gRPC library, right? If you're using it on both sides, then you could flip that on. And gRPC just I think went GA with their proxyless service mesh. And so you could use the control plane of a standard service mesh to talk to your gRPC libraries and tell them to do what they need to do to do the service mesh stuff. And now you don't have a proxy. So the proxy does add some latency, right? So that's why the people who build their proxies build them to be crazy fast. Linkerd, which is what we're going to use, is super awesome and has a Rust-based proxy. So compiled down to super compact, fast, native code. And Linkerd's kind of famous for being the fastest of the proxy-based service meshes out there. And it's also super easy to install and works really great. So the last lab, which I know there's no slide, lab 5, is going to have you install Linkerd and then start looking at some of the metrics, see how you can see connections and see them that they're secured. And it's really an amazing thing to see. And it's so easy to try out. So one of the shorter lab steps. So what I am going to do is say thank you a ton for coming. We do have another few minutes if you want to hang out to the bottom of the hour, but I think they will kick us out in like 3 minutes. So feel free to keep working on the lab up until the last if you want to, or work on it for lunch. We'll leave the boxes up for a bit. And yeah, thanks a bunch for coming. Have a wonderful rest of your convention.